Hey guys, I am Sri Rupra Chaudhary and welcome to the Intro to Machine Learning series by ISTE. Today we'll be going ahead with regression. Basically, we'll be looking at linear, quadratic, and logistic regression. The topics which we'll be covering throughout the video is regression versus classification, linear regression, polynomial regression, logistic regression, and lastly, linear versus logistic regression. Starting off with regression versus classification, let's dig in and see what classification basically here is. Well, in classification, the problem data is classified into one or two more classes, and a classification problem with two classes is called binary. More than two classes is called multi-class classification. It is quite similar to the dictionary meaning of classification to classify under a particular topic. So basically here we give an example of classifying a mail as spam or non-spam. Moving on to regression. Regression, basically the problem requires the prediction of the quantity, and a regression problem with multiple input variables is called multivariate regression problem. With regression, what we see is we look at the data set, the history of the data set, we look at the trends, and then we try to foresee what happens in the future. So it's basically price of a stock over a period of time, right? That's what is done with the help of regression. We try to find out the price of a stock, what it will be after 2 months or 3 months, by looking at the data sets of what we had previously. Moving forward, we have linear regression with us. So linear regression is a machine learning algorithm based on supervised learning, and it performs a regression task basically. And regression models a target prediction value based on independent variables. And it is mostly used for finding out the relationship between variables and forecasting. Different regression models differ based on the kind of relationship between the dependent and independent variables. They are considering the number of independent variable based being used, and also linear regression performs the task to predict the dependent variable value, which in most cases is y, based on a given independent variable, which in most cases is x. So this regression technique finds out a linear regression relationship between x and y, where x is the input and y is the output. Hence the name is linear regression. Well, a linear regression line has an equation in the form of y is equal to a plus bx, where x is the explanatory variable and y is the dependent variable. Here we have a typical graph on linear regression. Basically, as we have seen in the equation, it is b naught plus b1x plus e, where b naught is, if you see, is the y-intercept over here in the graph, and then we have b1, which is the slope of the best fit line, and e is the error. So basically, when we have a best fit line, it differs or deviates a bit from the points that we have. It does not perfectly lay on those points, so distance between the best fit line and the point is known as error. Now, to understand this algorithm, we have an example. We have the data set over here. What we do with it is first we try and find out the mean, and then with the mean we find out the m value. Once we have the m value, what we do is we should be given a c value, because we are going to place it as y is equal to mx plus c. So c in our case over here is 2.4, and m, what we have found out, is 0.4. So the equation of line which we obtain here is y is equal to 0.4x plus 2.4. Here it is, and then what we do is we plug in different values of x for y, and then obtain the values of y. Once we are done with that, we do plot it on our graphs. As we see over here, we have the x-axis with an independent variable and the y with a dependent variable. Here it is. We What we do is, this is our error. What we see, I did tell you in the previous PPT slide that the best fit line deviates a bit from the points which we have. So the distance between them is the error, and of course this picture shows the best fit line, and this is our regression model out here. Now what we have here is a small derivation about linear regression, of obtaining the the coefficients for linear regression. It's quite simple, you can go through it by pausing the video. Now what I have for you over here is a Python example that shows how linear regression works. So this is our Python code right over here, and then what we do initially is first we import the different libraries which are required over here, and well, NumPy is for all the processes which indulge in numbers and specific functions, I must say. And then matplotlib is a library which we would be requiring to plot points. So starting off with the program, we have estimate coefficient function where we define it. We have n is equal to np dot size, is basically it obtains the size of x, and then what we do over here is we find the mean of x and y, and then once we are done with calculating the mean of x and y, we calculate the deviation, and the deviation about x basically. And then once we are done with calculating the cross deviation and the deviation from x, we calculate the regression coefficients in a very similar way as we saw in the slides, and the function returns the value. Now what we have here is a plotting, the plot of the regression line over here. We define it. It's basically very simple. We have a scatter plot, and then we have what we do is we have the predicted response vector, then we have the plotting regression line and the plotting labels which are x and y, basically to show it on the graph. Then we come to the main function of the program, where we do give all the points or all the data which we want to, and we basically want to obtain the regression graph of this data set. Without wasting much of time, let's run this program and look what we have for us. So yeah, let's just run the program. Give it a second or two. Yes, here we are. So we do get the the coefficients for the for the formula, which is y is equal to mx plus c, and then b naught plus b1 x plus e. So b naught and b1 over here, once we do get that, this is the regression graph that we obtain. This is a typical linear regression graph that we obtain, and most of your, not most, all of your linear regression graphs will look like this. Moving back to the PPT, let's see what we have for us now. We have some important terms that we need to know while we go through regression. The first one is the mean square error, popularly known as the MSE, which is the average of the square of the errors. The lower the value, the better, and 0 means the model is perfect. Of course, we do need a zero most of the cases, which shows that the model is perfect and has no error in it. Then we have something known as the R2 score, which varies between 0 to 100%, and it is closely related to the MSE. And the R2 score, which is the total variance explained by the model by the total variance. That's how we obtain the R2 score. So a low R2 score would show the correlation, meaning a regression model that is not valid, but not in all cases, of course. Then what we have for us is polynomial or quadratic regression. Well, polynomial regression is a form of linear regression in which the relationship between the independent variable x and the dependent variable y is modeled as an nth degree polynomial. Polynomial regression fits a nonlinear relationship between the value of x and the corresponding conditional mean y. Now, and to know more about the polynomial quadratic regression, I would be stating some points. See, it is also called the special case of multiple linear regression in machine learning because we add some polynomial terms to the multiple linear regression equation to convert it into a polynomial regression. Then also it's a linear model with some modification in order to increase the accuracy, and also the data sheet used in polynomial regression for training is of nonlinear nature, and it makes the use of linear regression model to fit the complicated and nonlinear functions and the data sheets. To sum up all these points, what we do obtain for polynomial regression is that the original features are converted into polynomial features of required degree, which can be 2, 3, or the nth degree, and then modeled it using a linear model. Now, the polynomial quadratic regression has a very similar equation to that of linear regression, which is beta naught plus beta 1x plus beta 2x square. The only term extra we see here is beta 2x square, which makes it non-linear. So beta 1 and beta 2 are called the linear effect parameter and the quadratic effect parameter respectively. Considerations that we need to have in fitting a polynomial in one variable are as follows. Order of the model, order of the polynomial is kept as low as possible. Model building strategy, a good strategy should be used to choose the order of an approximate polynomial, increasing order, and test the significance of regression coefficients at each step of the model. Very important point one should keep in their minds while they're doing regressions, polynomial regression specifically, and then appropriate highest order model, and then delete terms one at a time, starting from the highest order. So we start from the nth order, and then we keep decreasing to an order when we have n is equal to 2, or lower than that n is equal to 1, but we usually stop at n is equal to 2. Extrapolation, which is very important. Hierarchy, well, a model is said to be hierarchical if it contains the terms x, x square, x cube, etc., and also it is expected that all polynomial models should have this property because only hierarchical models are invariant under linear transformation. This what you see on your screens is the typical basic regression polynomial regression graph that one would obtain. Now again, what I have for you is a Python program which shows polynomial regression. Again, a very similar approach. We start with NumPy and matplotlib. We do give the x and y values over here directly. What we do is we train the algorithm with the degree n is equal to 2 over here, and then we give the polyfit as the fitting considerations that we just discussed. And then we have plot data over here. We do line space for our convenience, then we plot it, we give it its style, we label the graph, and then the x-axis, y-axis, and everything, scatter plot that we want to obtain, and then we finally show the plot. So right, let's just run it asap. um, Here it is, quite quick. This is the polynomial regression graph that we have obtained. As you see, we have some errors. It's not completely perfect, but you won't find, you'll hardly find any polynomial graph with errors in it. Yeah, so this is the polynomial regression and pretty much sums polynomial regression over here. Moving to logistic regression that we have with us right now. So let me start with logistic regression. Logistic regression is basically a supervised classified algorithm. Its classification problem, the target variable, which can be the output, y, can take only discrete values from a given set of features. Features as in the inputs that we give to the model. The model builds a regression model to predict the probability that a given data entry belongs to the category numbered as 1. Just like linear regression assumes that the data follows a linear function. Logistic regression models the data using the sigmoid function. Well, in your screens, the last point is the sigmoid function, which is 1 by 1 plus e to the power minus z. Many books do show it as theta, so 1 by 1 plus e to the power minus theta. Well, the importance of logistic regression or the sigmoid function, I must say, is that whatever input you give, it squeezes the output between the value 0 and 1. It's basically calculating the probability with the given data sets. Now, how does logistic regression work? It takes your features and labels, fits it in a linear model. Instead of giving you the results, it gives you a logistic of the result. Now, based on the number of categories, logistic regression can be classified as binomial. Well, in binomial, the target variable can only have two possible types, which is 0 or 1, which may represent win or loss, pass or fail, dead versus alive, etc. Then we have multinomial, which the target variable can have three or more possible types, which are not ordered. Remember that, which are not ordered. It is disease A versus disease B versus disease C. And then we have ordinal, which is it deals with the target variables with ordered categories. Yeah. For example, it can be a test score, which is very poor, poor or good or very good, and each category can be given a score like 0, 1, 2, 3, etc. So yeah, this is how it is classified into these three forms. Well, before going to linear versus logistic, I again have a Python program. So here we have a program where it trains a logistic regression classifier to predict whether a flower is Iris virginica, which is a particular kind of flower, or not. So we start with importing as we did previously, then we set or we load the database with us, and then we do give x and y values here. I did filter it out because the data set is too huge and it'll take a lot of time to compute. It's just for our convenience. And then what we do is we call in the logistic regression function, which you can see over here. It's from sklearn. Sklearn is another library, to train data sets in machine learning. You can read the documentation, it's quite easy. And then we fit it with the points x and y, and then the value that we want to predict over here is with the value 2.6. And then what we do is we just plot it as we have been doing it for the other two programs. Running it real quick, let's see what do we obtain. So looks like it didn't run. Let's stop and rerun this. Yeah, giving it some time. Here it is. So if our given flower is Iris virginica or not, our value was 2.6. As you see, it's between the value between 0 and 1 only. 2.6 lies towards the right half of the graph, so it is more tending towards 1, so it is quite probable that our flower is Iris virginica. So here it is, logistic regression. That's it, that sums up logistic regression. And then moving to the very last part of our video, which is linear versus logistic regression. Linear versus logistic regression, as you see it from the graph, there are some basic differences. Well, in linear regression, it is used to predict the continuous dependent variable using a given set of independent variables. But in logistic regression, the logistic regression is used to predict the categorical dependent variable using a given set of independent variable. And also in linear regression, it is used for solving regression problems, whereas in logistic regression, it is used for solving classification problems. And in linear regression, we predict the value of continuous variable, whereas in logistic regression, we predict the values of categorical variables. Yeah, that's pretty much the difference. And the output of linear regression must be a continuous value such as a price, whereas the output of logistic regression must be a categorical value such as 0 or 1, yes or no, etc. Those are the basic differences, and as you see from the graph, it's quite evident that in linear regression we have a straight line, and then logistic regression we have a S curve as an output. and then the other parts, which are y and x, independent and dependent variables, remains the same. But in linear regression, the predicted y can exceed the 0 and 1 range, whereas the predicted y lies between 0 and 1 range in logistic regression. That pretty much sums up our video over here. I hope it will help you with the machine learning course which you are looking forward to take in the future, and this is just the very basic. Hope you have a great day, and thank you so much.